Hi friends, welcome back to our series of sessions on energy conservation aspects and industrial instrumentation related topics. Today, we shall be discussing about the electric motors, which play a very important role in every industry. Motors convert electrical energy into mechanical energy by the interaction between the magnetic fields set up in the stator and rotor windings. Electric motors are undoubtedly the largest prime movers used. Industrial electric motors can be broadly classified as induction motors, direct current motors, synchronous motors. All motors types have the same four operating components, which are stator windings, rotor, which has rotor windings, bearings, and frames. This is the completely split model of electric motor. We have the shaft, and then we have the rotor winding here. Then we have this is the stator winding all through. Then this is the terminal blocks. This is the cooling fan here, and this is the fan cover for the fan, and then end bell. Then this is the bearing of the shaft. This is the motor frame. This is the stator. This is the rotor. This is the rotor winding, and this is the rotor. This is the end bell. So this is the total disassembly of the electric motor, if you literally see. Then if you see the types of electric motors, there are various types depending on the types of construction. Due to difference in construction and their design, their applications also vary from process to process. There is a continuous technological development in the motor technology, and hence many types get outdated too. As we have seen, there are two types of electric supply. Similarly, to suit each of them, there are two types of motors also, DC motors and AC motors, alternating current motors and direct current motors. Industrial electric motors are generally classified into DC motors, synchronous motors, and induction motors, induced magnetic field induction motors. Then within direct current, we have separately excited and self-excited. And within induction motors, we have single phase and three-phase motors. And then self-excited, we have series motors, compound motors, and shunt motors. So if you see one by one, the direct current motors, the DC motors, were the first to be developed. They have a stationary field winding housed in a stator and rotating armature called rotor. This is an armature. The rotor winding rotate in front of alternating rotor poles, north and south poles. This tries to reverse the current in the winding. To overcome this problem, a commutator and brush arrangement is provided. Depending on the field and armature connections, the motors are classified as separately excited motor and self-excited motor, then series motor, compound motor, and shunt motors. Since these motors give different torque and speed characteristics, they are used for different applications. Example, series motors are invariably used in DC traction systems. Separately excited motors are used for applications where a high starting torque is required, and also where jamming is likely to take place and sudden torque requirement is likely to go up by 250% to full load torque. The speed control of DC motors is quite linear and accurate. The torque offered is uniform over the entire speed range. Because of these characteristics, they are still preferred in some of the applications. This is exactly what we have seen. The main advantage of DC motors is its speed control, which does not affect the quality of power supply. It can be controlled by adjusting the armature voltage. Increasing the armature voltage will increase the speed. The field current, reducing the field current will increase the speed. That is exactly what happens. The disadvantage of these motors are mainly their initial cost and maintenance of brushes and the commutator. Moreover, they require a separate cooling arrangement. That is also the major disadvantage of the DC motors. Then we have the synchronous motors. In these motors, the stator is given a three-phase AC supply. Rotor is given a DC supply through brushes and slip rings. The stator produces a rotating magnetic field, and a rotor field is locked into the synchronous of the rotating magnetic field. The speed of the rotation is given by synchronous speed is equal RPM 120 into frequency divided by number of folds. That's exactly what is the speed of rotation of synchronous speed that we see. The synchronous motor is not a self-starting motor. It has to be prepared to a speed near the synchronous speed so that the rotor gets locked with a stator and a rotator magnetic field. At one point of time in the history of technology, this motor was quite popular. The main advantage of this motor was that by controlling the rotor excitation, the power factor of the motor could be controlled, and the motor could be made to operate with a leading power factor. Hence, in the olden days, when a combination of the induction motor and static capacitor was not available, one big synchronous motor was provided to control the power factor of the entire electrical installation. They were even referred to as synchronous condensers rather than motors. The advantages evident of this motor, disadvantages of this motor are the slip ring and brush maintenance and provision for prime mover. The initial cost of these motors also was very high, but these days nobody opts to use these motors because of the total controls that we got in induction motors. Then we have the induction motors, which are the most commonly used prime mover for various equipment in industrial applications. In induction motors, the induced magnetic field of the stator winding induces a current in the rotor. This induced rotor current produces a second magnetic field which tries to oppose the stator magnetic field, and this causes the rotor to rotate. There are two types of induction motors, the slip ring induction motor and the squirrel cage induction motor. The slip ring induction motor, if you see, the stator is given a three-phase AC supply. The rotor is shorted outside through slip rings and brushes. Since the rotor connection is brought outside, an initial resistance of the higher starting torque can be introduced, and as the motor picks up speed, the resistance is slowly reduced and eventually shorted to make it zero. This arrangement that a starting torque of as much as 250% of full load torque can be obtained is an arrangement very common for loads like ball mill, hammer mills, etc. The disadvantage of this motor is slip ring and brush maintenance as usual. Then we have the squirrel cage induction motor, as we are seeing here. The squirrel cage rotor is rotating part used in most common from the AC induction motors. An electric motor with a squirrel cage rotor is termed a squirrel cage motor. By far, this type of motor has the largest population in industry. In overall shape, it is a cylindrical cylinder mounted on a shaft. Internally, it contains a longitudinal conducive bars, usually made of aluminum and copper, set into grooves and connected together at both ends by shorting rings, forming a cage-like shape. The name is derived from the similarity between these rings and bars winding and a squirrel cage. In this motor, the stator is given a three-phase AC supply. The rotor is shorted inside through the copper rings at either ends. When the stator is given a supply, it produces a rotating magnetic field which rotates at synchronous speed. The rotor then starts rotating, trying to achieve the synchronous speed, but it can never achieve it. The difference between actual speed and the synchronous speed is called slip. The slip, when represented in terms of percentage with respect to synchronous speed, is called percent slip. The formula is as follows. Slip percent is equal to synchronous speed minus full load rated speed into 100 by synchronous speed. So we are seeing this different. We have a stator here and we have a rotor, and then the shaft. The output power is here given. The input power is √3 VI cos phi, the electric power that we are giving. Output is given by omega n into torque. That's of the motor. Here we have the copper loss 0 to 4%, and iron loss 0 to 2%. We call them as eddy current loss and hysteresis loss. Then rotor copper loss 0 to 2%, and friction and windage loss 1%. So here we get rotor losses here, and then the stator losses here. And then the stator active power we are getting, and ultimately it current rotor active power, and ultimately it is the mechanical output power. So stray loss is around 1.8%. So this is the exact electrical energy balance of the induction motors that we are seeing. Then if you see, the stator is given a three-phase AC supply, and as we have just seen, the slip percentage is synchronous speed minus full rated speed into 100 divided by synchronous speed. From the above points, one must remember the following facts. The number of poles available in a machine will be 2, 4, 6, 8, and so on. Since the Indian standards for frequency is 50 Hz, the synchronous speeds available are 3000, 1500, 1000, 750 RPM. If a pole of 4-pole induction motor is running at 1470 RPM, the slip will be 30 and percent slip will be 2%. The advantage of these motors are simple construction, wide variety in application, practically no maintenance. That's the advantage. Then the squirrel cage induction slip ring motors, you see. That's the advantage, practically no maintenance and wide variety of applications. The power factor of the motor is given by cos phi, that is kilowatt by kVA. As the load on the motor comes down, the magnitude of the active current reduces. However, there is no corresponding reduction in the magnetizing current, which is proportional to supply voltage, with the result that the motor power factor reduces. With a reduction in applied load, induction motors, especially those operating below their rated capacity, are the main reason for the low power factor in electrical systems. Now let's understand the nameplates of the motor. And every motor leaves the factory with a specific nameplate. The nameplate contains information about the parameters mentioned, which are useful to understand the performance of the motor, which are nothing but rated voltage, the stator input supply. Then we have rated current, which gives the stator input supply current. This will occur when the motor is loaded fully to its rated output and rated supply voltage is applied. Then we have the rated output, which is basically the shaft power, which will occur when the full mechanical load is applied to the shaft. Rated speed is the shaft speed and will occur when the motor is fully loaded. Number of poles, this will decide the synchronous speed. Then the connection, whether it is a star or delta, this will decide the stator winding connections. And the rated power factor will occur when the motor is loaded fully and will occur at the stator point, input point. And the rated efficiency will occur when the motor is loaded fully and will indicate mechanical output power at shaft by input electrical power. These are the nameplate details of any electrical motor. Since it is not possible to load every motor at all times to operate at its rated capacity, most of the motors operate at partial loading, and hence it becomes necessary to study motor performances when they are partially loaded. It is at this stage of partial load that the performance of the induction motor is highly unpredictable and needs proper analysis to come to a definite conclusion so that energy can be saved. Because of the efficiency of motor is difficult to assess under normal operating conditions, the motor load can be measured as an indicator of the motor efficiency. As load increases, the power factor and the motor efficiency increases to an optimum value at around full load. The equation load is equal to PI into efficiency divided by HP into 0.7457, where efficiency is the motor operating efficiency, HP is the nameplate rated horsepower, Load is output power as percentage of rated power, and PI is the three-phase power in kilowatt. The load is measured basically in 3 steps. Step 1 is to determine the input power using the following equation. PI is equal to VI into power factor into root 3 VI cos phi. Cos phi is the power factor divided by 1000, where PI is the three-phase power in kilowatt. V is equal to RMS root mean square voltage, mean line to line of 3 phases, I RMS current, mean of 3 phases, and power factor as a decimal point. That's how we are putting this. It is noted that power analyzers give the power value directly. Industries that do not have a power analyzer can use multimeters or tongue testers to measure voltage, current, and power factors separately to calculate the input power. Then step 2 is to determine the rated power by taking the nameplate value or by using the following equation. Rated power is equal to HP into 0.7457 divided by efficiency, rated efficiency, where PR is the input power at full load in kilowatt, HP is the nameplate rated horsepower, and NR is efficiency at full rated load. Nameplate value are from motor efficiency tables. Then the step 3 is to determine the percentage load using the following equation, PI by PR into 100%, whereas load is equal to output power as percentage of rated power. PI is measured three-phase power in kilowatt input power. PR is the rated input power at full load in kilowatt. And based on this, we can find out the motor. So once we arrive at all these motor loading points, then we can go for calculating the motor efficiency and its losses. Electrical motor efficiency, when shaft output is measured in watts, is given by Nm by P out by P in. If power output is measured in watt, efficiency can be expressed as P out by P in, where Nm is equal to motor efficiency, P out is the shaft output power in watts, P in is the electrical power given to the motor in watts again. Thus, if one can concentrate on assessing losses and trying to reduce them, then efficiency can be increased. Hence, it is pertinent to study what losses do occur in a motor. The losses can generally be classified into 2 categories, fixed losses and variable losses. Fixed losses are those which occur in the motor irrespective of quantum of load. These are called no-load losses. Fixed losses, then variable losses we have are those which are dependent on the quantum of load. Since the current drawn by the motor is a function of the load, both stator and rotor copper losses are variable losses. They occur by way of heat loss equal to I square R, where I represents current and R represents resistance. Hence, they are dependent on stator and rotor resistance. The value of stator resistance in turn is dependent on temperature. Then we have the no-load test. Ambient temperature can be measured by an accurate multimeter or Wheatstone weights. There are 2 important tests to be carried out on the motor, based on which its performance at partial load can be calculated with the help of a circular diagram. No-load test gives the fixed losses of the motor. The motor is run on a decoupled condition by applying the rated voltage, and parameters like current and voltage are measured. Then we have a blocked rotor test. For this test, the rotor is blocked and with reduced load voltage, a full load rated current is circulated through the stator. At this time, voltage applied is measured along with the power drawn, that is in wattage. These parameters are extrapolated for full load voltage, and based on the extrapolated parameters, a diagram is drawn called a circle diagram. Once the circle diagram is drawn, the performance of the motor at any partial load can be assessed, but this method is used in the design office or at the test bed and is rarely used at site. The mechanical losses such as friction and windage losses are fixed losses depending on bearings and aerodynamic losses associated with the ventilation, fan, and other rotating parts. Stray load losses are difficult to measure and are taken as thumb rule based on certain standards. Then factors affecting motor performance, it depends on partial load operation correct application of the drive to suit the application, and then application of rated voltage and frequency. So these three are very important factors affecting motor performance. Performance of an induction motor on partial load can be seen from the graph. It will be observed that the best performance of the motor is nearer to the rated output. The power factor is also improved as the load approaches the rated load. Hence, the performance of the motor depends very much on the load on the motor. Thus, loading a 10 HP motor with 9 HP load is far superior than loading a 15 HP motor with 9 HP load. That's exactly what we understand. In that case, it is worthwhile to replace a 15 HP motor with a 10 HP motor. The economics of replacement will always be in favor of replacement, which will ensure near rated load operations. Then if you see the rewinding of these motor replacement issues, it is general exercise in industry to rewind burnt out motors. Many a times during the maintenance of motors, one has to encounter rewinding of motors. The rewound motors seldom give the same performance as original motors. This is mainly because the gauge of the wire used for rewinding is rarely the same. The characteristics do not remain the same for after rewinding. No load motor and full load current also undergo unchanged. Due to this, every time a motor is rewound, its useful life is affected and the next rewinding is advanced. Hence, a stage comes when replacement is more economical than rewinding. Hence, motors rewound must be checked thoroughly before loading them to its original loading pattern. One standard method to measure the stator winding resistance before and after rewinding. It is also a good practice to keep a record of the no load current prior to and after rewinding. These two parameters do speak about the condition of the rewound motor. In fact, in many factories, the payment of the rewinding contractor is linked to these two parameters, and the motor is rejected after rewinding if the no load current exceeds the predefined value. That is exactly what we have been seeing. Then, based on these motor replacement issues, everything, energy saving opportunities with energy efficient motors can be considered, because energy efficient motors are the ones in which design improvement are incorporated, especially to increase operating efficiency over motors of standard design. It is important to know what energy efficient motors is, and as it takes care of the shortfall in efficiency. Energy efficiency motors were defined by National Electrical Manufacturers Association NEMA standards in the US, first under the Energy Policy Act, and then trend was followed by other countries. In India, Bureau of Indian Standards defines EEM as those which operate without loss of efficiency from 75% load to 100% load. Moreover, the mounting and overall dimensions are designed as per IS 1231, making it easier to replace the standard performance motors with energy efficiency motors. While selecting a motor for any application, an engineer should keep a margin of about 20% in motor rating. Energy efficient motors automatically take care of the shortfall in efficiency. Many a times, economics have proved that even an existing running standard performance motor can be replaced with energy efficient motor with a payback period of as low as 18 months. Then the figure here shows the comparison between energy efficiency and standard motors. We will see this is the efficiency of energy efficiency motors at different rated voltages for a 75, whereas for standard motors, we see the efficiency is very less when we use the motors at a very low rated capacity, because that's the reason when we have a 10 kilowatt motors have to be rated at 10 kilowatt, and whereas we should not use a 50 kilowatt motor to be used at 10 kilowatt rating. So this is exactly for a typical three-phase induction motor, the efficiency and power factor versus load. And so every motor has always to be rated or loaded at its highest rating. That is very, very important. Then we have it is important to know how energy efficient motors are different from standard motors. Efficiency can be improved by reducing standard losses. Thus, energy efficient motors are designed so that these losses are reduced. So this table describes the improvement opportunities that are often used in the design of energy efficiency motors. Then the state power loss area is stator and rotor copper losses. Then the efficiency improvement is these losses are reduced by using copper instead of aluminum wherever possible. Then the magnetic losses of the stator are reduced by reducing the air gap. Core losses are reduced by using the thinner material. Also, low loss silicon steel is adopted. Friction and windage losses are reduced by using better bearings and better cooling fans. And stray losses are reduced by better designing geometry of the motor. So energy efficiency improvement used in energy efficiency motors as prescribed by Bureau of Energy Efficiency in India in the year 2000. So that's all about the motors. Hope you have enjoyed this session. See you soon. Thank you very much.